Leland Sutter, and I'm a geospatial data analyst within the corporate tailings, crush, leach, and water team, also known as TCLW at Freeport-McMoRan. My first question whenever I tend to talk is, who is this person and what does this person do? Well, I went to the University of Arizona where I received my master's in geography, in which I used drones to conduct machine learning on plant regrowth following a 2017 fire right south of Tucson. I'm heavily rooted in ecophysiology, plant physiology, and remote sensing research. The very first question I'm always asked is, how did I end up at a mining company? Here at Freeport-McMoRan, we use imagery. And that's really an understatement because we use a lot of imagery. Moving through this presentation, you'll see that we leverage a variety of data sets, both public and commercial, to address a variety of questions with the most important topic on all of our minds, safety. So what are we going to talk about? In the next 20 minutes, I'm going to move through an introduction of who we are as a team, how we use remote sensing technologies, some data sets that we use to answer those questions, talk through the uses that we initially thought of when we were presented with planet imagery, additional uses that we found, a few case studies, and then I'll conclude with some parting thoughts. And who are we as a team? TCLW is a multinational, interdisciplinary team based out of Phoenix, Arizona, working across continents, languages, and cultures. We support and manage tailing storage facilities across North America, South America, and Indonesia. Pictured here are our current active sites. However, we also have many closed facilities that we continue and will continue to monitor far into the future. Our team includes experts such as geotechnical and water resource engineers, geologists, hydrologists, geophysicists, geomorphologists, metallurgists, data scientists, and remote sensing scientists. You'll see us at conferences presenting or in classrooms teaching. Guiding our group is Tamara John Dro, Georgia Lysay, Mark Schmelter, and Teresa Spiegel. Collectively, they represent a diverse set of skill sets, bring decades of experience to the group, and are currently serving on various international professional organization committees. Spearheading technology initiatives, Mark Schmelter leads the corporate TCLW geospatial team that includes Michael Wallace and myself. Mark Schmelter has a PhD in civil and environmental engineering and a master's in statistics, and Michael Wallace has a master's in geophysics. Due to the inherent geospatial nature of our fields, we have taken on the technology and geospatial initiatives within TCLW, implementing geospatial practices that have been adopted across multiple groups company-wide, as well as advising third-party vendors on specific data needs. Freeport-McMoRan is committed to zero catastrophic failures or unplanned discharges from TSFs. We accomplish this through communication and action in engineering and design, monitoring and technology, multi-tiered oversight, and learning from past experiences. For more detailed information, our annual sustainability report can be accessed online at our company's website. So within this context of this presentation, how can we use remote sensing technologies? Some examples include where and how much water is in our facilities, are there anomalous features on our facilities, and how can we monitor in a way that is efficient, holistic, and most importantly, safe? Looking at monitoring and technology, and more specifically remote sensing, there are an array of both public and commercial platforms that we utilize daily. Most are familiar with the Landsat and Sentinel constellations. We also use state and local data sets, commercial satellites, aerial campaigns, internal and external UAS surveys, and now Planet. Of course, as we begin to look at how we utilize these tools and data sets, there are inherent strengths and weaknesses found within each one. High level, we can begin to look at how each one within the context of resolution and costs. Here, we have spatial resolution. How well can we spatially resolve objects or features on the ground? We typically think of this by the size of the image pixels. Spectral resolution. How many bands does each data set have, and how wide are those bandwidths? To discriminate a variety of soil properties, we need spectral bands that can reach beyond just the visible range. In addition, subtle changes in those properties require those bands to be precise. What is the frequency at which data is collected? Return time is extremely important when thinking about the dynamic conditions of mining and the many projects that are happening simultaneously. And finally, what are the general costs? This can range from free to many thousands of dollars. Ultimately, no one platform or data set will answer every question. With trade-offs made for every project that we work on, this is not a comprehensive list, and arguments could be made about emerging technologies, such as the development of hyperspectral cameras on unmanned aerial systems. However, one must remember that decision makers require practical solutions to problems with results that can be repeated in a timely fashion. Free datasets are shown in blue and paid, commercial, in orange. When thinking about initial project planning, expensive commercial products are not necessarily the best tools for that particular job. There are many amazing free datasets available, and now PlanetScope. One example of this is seen with Sentinel-2 and Planet when looking at the normalized difference wetness index in DWI. Sentinel-2 on the left has a spatial resolution of 10 meters and return time of 5 days. Planet has a spatial resolution of about 3 meters and mostly a daily return. Both are extremely similar and very useful in pulling water bodies. However, NDWI becomes saturated quite quickly, and without the addition of a shortwave infrared band, a SWIR band, it is impossible to discriminate soil moisture in such a robust manner as seen with Sentinel-2 on the left, using the normalized difference moisture index, NDMI. On the left, we can see the flow direction with expected deposition to the center pond. On the right, without the SWIR band, we cannot uniquely discriminate some areas. So let's shift gears to planet imagery. When presented with this high temporal medium spatial resolution data set, we immediately thought of water body extraction. We know that we can gain basic information about soil moisture with multispectral data, so we immediately set our machine learning scripts to work on this imagery. Initial questions were focused on where water is located and where it is going. We also wanted to see if we could find wet and dry areas on our facilities. As COVID-19 spread across the world, we, just as many other companies, were forced to operate at reduced capacity. This meant that we need to be even more vigilant in our remote inspections. We've had a pipeline for Sentinel-2 coverage over our sites, but Planet gave us an extra layer of monitoring. Here in Peru, we were operating at reduced capacity, and governmental stay-at-home orders meant that we could not have the normal numbers of inspections on the ground. We leveraged near-daily Planet imagery to map water in our facility and built online maps and dashboards so that operations in Peru could adapt their processes. Visibility was increased for engineers, operators, and other decision makers both on and off the site. Other sites have taken to the imagery online to monitor the location of their ponds in relation to the outer slope of the embankment. Having daily imagery allows engineers on site to monitor the location of these ponds to more efficiently plan their daily work. Without remote sensing technology, water on these large facilities must be measured on the ground with markers and rangefinders. Think of trying to do this on a dam crest that can be a mile long. Engineers in emergency can simultaneously gain a better understanding of water location while staying safe. Working with Planet software developers and product owners, we've seen a huge improvement in online visualizations. This both minimizes the amount of data that must be downloaded while also improving the speed at which users can make decisions. Here, they are mapping a weekly NDWI index, which is useful for looking at water body location trends. Development is continuously ongoing, so we're always excited to see what's next. Some sites experience significant cloud cover for large parts of the year. Inclement year-round weather is common at the site in Colorado. When we combine daily Planet imagery with other satellites, there's a higher chance that an image can be acquired. Events of interest, such as spring melt-off, can now be more easily tracked. Back to online integration, our corporate GIS analysts and developers serve up imagery within an Esri portal environment to the entire company. We've been able to integrate web map services, WMS layers, to supplement other data sets. WMS layers are then integrated with other online applications that require imagery, ultimately assisting with visibility over site-specific projects. Other groups, such as our environmental group at Cerrita, uses this imagery to identify potential dust generation areas at weekly meetings. They can plan inspections to walk the impoundment and respond to requests from regulatory bodies, which in this case is the Pima County Department of Environmental Quality. PDEQ. Although this imagery is not required as part of the air quality permit, using this imagery is appreciated by PDEQ. Next, we'll look at two more specific use cases. Giving some faces to our corporate water team, the team leader is Brant Whiting. He has his master's in civil and environmental engineering, has been working within civil engineering for 15 years, and here at Freeport with the North and South American sites for 7.5 years. Hong-Lin Kim has a PhD in water resource engineering from Utah State University. He has worked at the Department of Natural Resources as a hydrologist and has been working with Freeport for 3 years. Craig Pizak has a master's from the University of Pennsylvania in engineering geology and has also been with Freeport for 3 years. Together, this team manages water resources across our North and South American sites. Water balance modeling and accounting is a primary focus of this team. These models rely on estimates of actual pond volumes in order to aid in model calibration. And because water pond areas are related to volumes, measured pond areas can be used as one such calibration metric. Historically, water model calibration has relied on 50-centimeter quarterly world view imagery for calibration. As seen by the red dots, a calibrated line representing historic pond areas can be fit with this imagery. By including imagery from Planet, we're able to more robustly calibrate and validate our water models because we have more observations. Barge locations, beach width, and deposition, among other variables, can be tracked. The more intricate peaks and valleys inferred from the water models can be validated with pond areas derived from frequent revisit times of PlanetScope. And in combination with weekly multispectral analysis, water models can be calibrated and reported to site operations. Our mine in Chino, New Mexico was shut down because of COVID-19. However, we must still monitor our facilities for safety. As part of water management activities, Homan has been using machine learning to classify the pond and to calculate water surface area. He has then created a web application that is used by on-site operations to quantitatively track water in near real time. Using this information, adjustments can be made on upstream and downstream processes. In conclusion, we have a company-wide commitment to safety. We use an array of remote sensing data sets that are both public and commercial. Each platform has its own unique strengths and weaknesses. No one tool can provide all the information we need and use. We see many future opportunities with Planet. Web development and introduction of cloud computing has been positive, with an eventual goal of minimal downloads for on-the-fly visualizations. Expected increase of spatial resolution of SkySat will give greater flexibility for imagery needs on our sites. Increased spectral resolution beyond NIR into SWIR would allow for better discrimination of soil surface properties. Use cases are always developing, with new ideas being generated as groups are introduced to new sources of imagery. We're always looking for the latest technological trends to meet and exceed our safety and production goals. PlanetScope imagery is a great solution for high temporal, medium spatial resolution imagery. Safe, holistic monitoring is accomplished through multidisciplinary collaboration. No one technique of technology can answer every question. Thank you.